विद्यार्थी मित्र हो, आज आपण भौतिकशास्त्रामधील हीटिंग इफेक्ट ऑफ करंट या विषयावरती चर्चा करणार आहोत. माझं नाव डॉक्टर वर्षा जोशी. मी पुण्यातल्या नवरोजी वाडिया महाविद्यालयामध्ये 30 वर्ष भौतिकशास्त्र शिकवण्याचं काम केलं. 2003 साली मी रिटायर झाले. त्यानंतर आता विज्ञान विषयक लिखाणाचं काम करते. माझं वाद्यांमधील विज्ञान हे पुस्तक प्रकाशित झालेलं आहे आणि स्वयंपाकघरातील विज्ञान हेही पुस्तक प्रकाशित झालेलं आहे. विज्ञान सौंदर्य प्रसाधनातील हे पुस्तक प्रकाशनाच्या वाटेवरती आहे आणि सध्या साप्ताहिक सकाळमध्ये वस्त्र आणि विज्ञान, वस्त्रांमधील विज्ञान हे सदर किंवा ही लेखमाला मी लिहिते आहे. विज्ञान विषयक लिखाण करणं ही माझी आवड आहे आणि आपल्याला सगळ्यांना हे पटेल की या सगळ्या गोष्टीमध्ये रोजच्या जगण्यामध्ये आपल्या भौतिकशास्त्राचा जिथे तिथे संबंध येतो आणि त्यामुळे तो जाणून घेणं हे अतिशय आवश्यक आहे. आजचा जो आपला विषय आहे हीटिंग इफेक्ट ऑफ करंट, याच्याबद्दल आपण बोललो की तेव्हाही तुम्हाला समजेल की ह्याचा आपल्या खरोखरच रोजच्या जगण्याशी संबंध आहे. तर सुरू करूया आता हे समजून घ्यायला. ज्या वेळेला कळलं की विद्युत प्रवाहाचा अनेक गोष्टींशी संबंध आहे आणि त्याच्यामुळे अनेक गोष्टी साधल्या जातात, तेव्हा त्याच्यावरती अभ्यास करायला सुरुवात झाली आणि असं दिसलं की रेझिस्टन्सचा रोल काय आहे इलेक्ट्रिकल सर्किटमध्ये. तर जसा घर्षणाचा रोल आहे, रोल ऑफ फ्रिक्शन इन मेकॅनिक्स, घर्षणाचा जसा रोल असतो तसाच हा रोल आहे. म्हणजे कसं की हे घर्षण ओव्हरकम करण्यासाठी आपल्याला काय करायला लागतं, तर मेकॅनिकल एनर्जी इज टू बी युज्ड. सिमिलरली in case of electricity, when current flows to a conductor, it offers resistance to the flow and work has to be done by the current continuously to keep itself flowing. This work is electrical energy which is converted into heat energy. म्हणजे ज्याप्रमाणे फ्रिक्शन ओव्हरकम करण्यासाठी आपल्याला मेकॅनिकल एनर्जी किंवा मेकॅनिकल वर्क हे करावं लागतं, त्याचप्रमाणे इलेक्ट्रिकल फ्रिक्शन ओव्हरकम करण्यासाठी आपल्याला इलेक्ट्रिकल एनर्जी ही सप्लाय करायला लागते. रेझिस्टन्सचं फ्रिक्शन ओव्हरकम करण्यासाठी इलेक्ट्रिकल एनर्जी सप्लाय करायला लागते, विच इज द वर्क डन. मग आता हे वर्क डन म्हणजे किती आहे किंवा कसं कॅल्क्युलेट करायचं ते पाहूया. लेट अस therefore calculate the work done by a current I when it flows through a resistance R for time t. When an electric charge Q moves through a resistance R for time t, and when an electric charge Q moves through a potential difference V, the amount of work done W is given by W equal to Q multiplied by V. म्हणजे Q हा चार्ज आहे, V पोटेन्शियल डिफरन्स आहे, R हा रेझिस्टन्स आहे आणि T हा टाइम आहे. तर वर्क डन म्हणजे चार्ज गुणिले पोटेन्शियल डिफरन्स. From the definition of current, we know that I equal to Q by T. Current is rate of flow of charge. Therefore, charge equal to I multiplied by T. From Ohm's law, we know that V divided by I is R, or V equal to I multiplied by R. These two equations are the ones that we are using, and we substitute them in equation 1. Let us see what was equation 1. Equation 1 was W equal to Q into V. So we are substituting for Q and V. So when we substitute, we get W equal to I multiplied by T multiplied by I multiplied by R. I multiplied by T is Q and I multiplied by R is V. That is what we have substituted. So W equal to I square RT. This is what we get as the work done. If we assume that all the work done is converted into heat energy, then we can write that the heat produced H is given by H equal to I square RT joules. Amount of heat produced किती आली? करंटचा स्क्वेअर गुणिले रेझिस्टन्स गुणिले टाइम T. ह्या नियमाला म्हणतात Joule's law of heating. This is known as Joule's law of heating. According to this law, the amount of heat produced in a conductor is directly proportional to the square of the current passing through it, the resistance of the wire, the amount of time for which the current passes through it. म्हणजे करंटचा स्क्वेअर, वायरचा रेजिस्टन्स आणि किती वेळ करंट त्याच्यामधून गेला याच्यावरती किती हीट प्रोड्यूस झाली हे अवलंबून असतं. This means keeping R and T the same, larger is the current passing through the conductor, larger will be the amount of heat produced, and smaller is the current passing through the conductor, smaller will be the amount of heat produced. The dependence of this heat on these various parameters is what we saw. It should, however, be noted, this is very important, that all the appliances that run on electricity do not convert all the electric energy into heat energy. For example, when current passes through an electric fan, most of the electric energy is converted into rotation of the blades of the fan. Only a very small amount of electrical energy is converted into heat energy by the fan. When a ceiling fan is continuously rotated for a long time, when it runs continuously for a long time, you can touch the fan and feel that it has become slightly warm. It doesn't get heated as the toaster gets heated or the electric heater gets heated, isn't it? Therefore, not in every appliance the total electrical energy is converted into heat energy. In electrical heating appliances like electric heater, kettle, geyser, iron, toaster, oven, all of the electrical energy is converted into heat. All of these electrical appliances have heating element or heating coil made of high resistance wire such as Nichrome wire. Nichrome is an alloy of nickel and chromium. Alloys always offer more resistance to current rather than pure metals, and that is why they are preferred. We just saw that the work done is converted into heat. The rate at which the work is done in maintaining the electric current is called electric power. Therefore, power P is given by P equal to W upon T equal to I square RT upon T equal to I square R. Substituting from equation 3, let's see what was equation 3. Earlier, the equation 3 was V equal to IR. Let us go back and find out what was equation 3. V equal to IR. So substituting from equation 3, we get P equal to I square R equal to VI equal to V squared upon R. The unit of electric power is watt. The unit of electrical energy is joules, and the power is rate of doing work. Therefore, it will be energy upon time. Therefore, 1 watt is 1 joule per second. Let us now solve some problems based on these equations. A 10-volt storage battery of negligible internal resistance is connected across a 100 ohm resistor made of nichrome. How much heat will be produced in 1 hour? What is the source of this energy? Let's see what are the quantities given. Here R is 100 ohms, V is 10 volts, T is 1 hour, which is equal to 3600 seconds. Always remember that time should be taken in seconds. Whenever it is given in hours or minutes, you have to convert it in seconds. Current I is V by R. Therefore, it will be 10 divided by 100, that is 0.1 amperes. Heat produced will be I square RT. Therefore, that will be 1 upon 100 into 3600, which gives us 3600 joules. And what is the source of all this energy? The voltage difference is provided by the battery. So, the current is supplied by the battery. And this current is generated in the battery by the chemical energy. So, the source of energy is the chemical energy in the battery. Let us consider problem 2. A thin metallic wire of resistance 100 ohms is immersed in a calorimeter containing 250 grams of water at 10 degrees Celsius and a current of 0.5 amperes is passed through it for half an hour. If the water equivalent of the calorimeter is 10 grams, find the rise in the temperature of the water. Once again, let's see what are the quantities given. R is given to us as 100 ohms, current is 0.5 amperes, time is half an hour. Again, see, we have converted that into 1800 seconds. What will be the heat produced? It will be I squared RT. So that will be equal to 0.5 square into 100 into 1800. That is 4.5 into 10 raised to 4 joules. Now water equivalent of calorimeter is 10 grams. We are working in SI system of units, so we will have to convert that into kilograms. So that will be 10 raised to minus 2 kilograms. Mass of water is again given in grams, 250 grams, which is converted into kilograms as 0.25 kilograms. Let us suppose that theta is the rise in temperature. What will therefore be heat absorbed by the water? It will be the mass of water plus water equivalent of calorimeter multiplied by the specific heat of water in SI system multiplied by the rise in temperature. That's why we get this equation as 0.25 plus 0.01, the whole thing multiplied by 4.2 into 10 raised to 3 into theta joules. Heat absorbed by water equal to heat produced by current. So 0.26 into 4.2 into 10 raised to 3 into theta is 4.5 into 10 raised to 4. When we work out the mathematics, we get rise in temperature as 41.2 degrees Celsius. One more problem. A potential difference of 250 volts is applied across a resistance of 1000 ohms in an electric iron. Calculate the current and heat energy produced in 10 seconds. The quantities given are potential difference equal to 250 volts, resistance equal to 1000 ohms, time t equal to 10 seconds. What will be the current I? It will be V by R, so that will be 250 upon 1000, that is 0.25 amperes. How much will be the heat produced? It will be I square RT, and therefore it will be 0.25 square into 1000 into 10, and that gives us 625 joules. Let us now see some applications. Applications of heating effect of current. The major and foremost application is electrical heating appliances. Electrical heating appliances such as electric kettle, electric iron, toaster, oven, heater, geysers. These are the instruments that we use in our everyday life. These have coils of wire made of nichrome alloy, which has high resistance. When current is passed through these coils, heat is produced due to the high resistance. The temperature of the heating element is about 900 degrees Celsius when it becomes red hot and glows. Here are some examples of the electrical appliances which make use of heating effect of current. The first one over here is the electric iron. You can see that this is the heating element. From this wire, the current passes through this heating element and the element gets heated. There is a thermostat over here also, which is not shown in this figure, but that thermostat keeps the temperature constant, the temperature that we adjust on the iron. But this is the nichrome coil or nichrome ribbon which gets heated because of current passing through it. Over here is the electric heater. You can see once again this coil made out of nichrome. Once again the current passes through this and the wire gets heated. There is usually a plate on top of this, which is a conducting plate, conducting heat, not electricity. And therefore that plate gets heated and we can put our pots and pans on that and cook on this. This is the electric kettle, which is used for heating water. Once again, it has a heating element through which the current passes and it gets heated. This is immersion heater. You can put it in the bucket and your water can get heated. Once again, there is a heating element over here through which the current passes, and that is how it gets heated. So these are some of the examples of appliances which make use of this particular concept. Second example is electric lamps. When electric current passes through a very thin high resistance tungsten filament of an electric bulb, the filament becomes white hot and emits light. Tungsten is used for making filaments because it has a very high melting point of 3380 degrees Celsius. When electric current passes through the filament, lots of heat is generated due to its high resistance. Remember that Thomas Alva Edison discovered the lamp and made use of almost 1000 different types of filaments till he reached the conclusion that tungsten is the best option available. Over here is a picture of a bulb which has this tungsten filament. We can see over here, this is the glass bulb and this is the tungsten filament. Now it needs some support, so these are the support wires that are provided. And this is the glass mount. Over here what you have is screw thread contact, and over here what you have is insulation. This is the electrical foot contact. From here the electricity or current is supplied which passes through the filament. The filament gets red hot and then white hot and starts emitting light. Over here we can see that this bulb has got inert gas in it. We are going to see now the reason as to why the bulb has inert gas in it. Due to the high melting point, the filament becomes very hot, that is white hot, and emits light but does not melt. Why? Because it has got a very high melting point, 3380, and over here it is written that when it emits light, its temperature is about 2500 degrees Celsius. So tungsten has high flexibility, low rate of evaporation at high temperature, and when it emits light, its temperature is 2500 degrees Celsius, which is very less, quite less rather, as compared to its melting point. If air is present in the bulb, the extremely hot tungsten filament would burn quickly due to the oxygen in the air. Therefore, electric bulbs are filled with a chemically unreactive gas like argon or nitrogen or a mixture of both. The life of the bulb is thus prolonged. So, the picture that we saw of the glass bulb contained inert gas. We now see the reasoning for that. The third application of the heating effect of current is electric fuse, which is very, very essential in all our appliances as well as in our domestic circuits. The household wires and electric appliances need protection against high current passing through them, which could cause damage. A fuse is used for this purpose to avoid this damage. A fuse is a short length, thin, tin-plated copper wire having low melting point. This wire has a higher resistance than the rest of the electrical wiring in the house. Here is a picture of the fuse that generally is used in our domestic circuits. When excess current flows in a circuit due to short circuit or any other reason, the fuse wire gets heated and melts. As a result, the circuit breaks and current stops flowing. This prevents fire, which could be caused due to overheating of wirings, and also prevents damage to various electrical appliances in the house due to excessive current flowing through them. So this is how the fuse protects us from hazards of fire as well as protects our instruments from any damage. After going through all this discussion, some questions come to our minds. Let's see the answers to them. We saw that in all the heating appliances, when current passes through them, they become hot. But to pass the current through these appliances, we need connecting wires. Why don't the connecting wires become hot and glow or melt? The answer to this is, the connecting wires are usually made of copper or aluminium, which are very good conductors, and therefore they have very low resistances. Due to the low resistance, the amount of heat produced is extremely small. That is why they do not become hot, and that's why they do not glow, and they do not also melt. Second question. Why is the length of a fuse wire immaterial? The material of the fuse wire, the radius of the fuse wire, that is area of cross section, are all important things. But the length doesn't matter very much. Why? Let us see the answer. For that, let us do some derivation. Let there be a fuse wire of length L, area of cross section A, that means the radius is R, and resistivity of the material is rho. Therefore, what will be the resistance? The resistance of the fuse wire will be rho into L upon A. But area of cross section is pi r square, so this becomes rho L upon pi r square. Let I be the current passing through the wire. Therefore, heat produced per second will be I square R, which will be I square into rho L upon pi r square. Now let us find out what is the surface area of the wire. 2 pi r is the circumference and L is the length. Therefore, surface area of the wire will be 2 pi r L. We are assuming that the wire is cylindrical. So, surface area is 2 pi r L. If H is the rate of loss of heat due to radiation from the wire per unit surface area, why do we have to consider this rate of loss of heat? Because the wire is getting heated, at the same time it is losing its heat to the surroundings. And when this equilibrium is not maintained, the heat in the wire becomes excess and it is going to melt. Therefore, we have to find out the condition for that equilibrium. And therefore, we need to know the rate of loss of heat due to radiation from the wire per unit surface area, that is H. So, if the surface area is 2 pi RL, then heat lost per second by the wire will be 2 pi RL into H. In equilibrium, heat lost must be equal to the heat gained per second. So 2 pi RLH equal to I square R. But I square R will be I square rho L upon pi R square. Therefore H is I square rho upon 2 pi square into R cube. Now rho and pi are constants. Therefore heat which is lost per second is proportional to I square upon R cube. Now this expression doesn't have L anywhere. So rate of loss of heat which increases with temperature does not depend upon L, and therefore L becomes immaterial in case of a fuse. Therefore these are the different applications that we have seen. Different questions that came to our mind that we have seen. One more question is there. Why an electric bulb is not power efficient? In a bulb, most of the electric power is converted into heat. Only a small amount of electric power is converted into light. Now, how do we calculate the efficiency? The efficiency is the amount of power actually used, divided by the total power that is input. Now, since only small amount of power is converted into light, naturally the efficiency will be small. Therefore, an electric bulb is not power efficient. What are the characteristics of a heating element and fuse wire? A heating element should have high resistivity and high melting point, whereas a fuse wire should have high resistivity and a low melting point. So these are some of the points that we have to remember. It has been a pleasure to talk to you about heating effect of current. Thank you.